Thanks for holding with us, everyone. I'm Ben Treese, the team lead of Project ROLR, and we're going to be talking to you about our PDR. So first I'm going to introduce the team. We have Nicole Lopez, John Daniels, Braxton Kendall, Austin Mikowski, and Kyle Bergman. So to talk to you about our purpose, what exactly we're trying to do with Project ROLR, we're trying to design an alternative form of planetary rover locomotion. So traditional planetary rovers have exposed drive mechanisms and a limited scientific payload. That is, you get one scientific payload per rover. With our design, we're trying to make an enclosed system which has numerous benefits that we'll go over later, and then also has a modular scientific payload. So up on the screen you have Curiosity, which demonstrates the traditional rover style that is currently being used, and this is BB-8, the concept origin for our rover. And here's the original concept drawing. You have the internal workings of the beam that modulates the head, batteries, tube, motors, and the head module containing all the scientific equipment. So to go over our overview for the rest of the presentation, we're going to talk about our system through Project ROLR's system objective and requirements. Then we're going to cover our Project ROLR overview, our concept of operations, what exactly ROLR is trying to accomplish during a normal mission cycle. And then we're going to go through each individual subsystem, that is through our requirements, the design of that subsystem, and then Project ROLR's system design. Finally, we're going to have some concluding remarks where we're going to cover our requirement satisfaction, the project's budget, any lessons that we've learned throughout the semester, and special things. So I'm going to go ahead and pass it off to Nicole Lopez, and she's going to talk to you about our system level requirements.
All right, thanks, Ben. As he said, I'll be talking about our system definition concept. So to start, we'll go over Project ROLR's objectives, and these objectives, we have 5 primary objectives. The first one is that it should explore a planetary surface simulated by Roller Hill. So this is Roller Hill. It goes along, on this Prescott campus, along Darbertine Drive, up until, from the bottom of the parking lot, up this hill to the top of the parking lot and back down, and that'll be 1 lap of Roller Hill. It also consists of our base station that's at the beginning of Roller Hill and the operator on the side of it, just to separate the operator and the base station. So the second and third, or second primary objective is that it will have an enclosed drive system, and ROLR should also collect and communicate data in real time with an operator so that the operator can drive and see what's going on. Our last primary objective is that ROLR will go to a base station to recharge in between each lap of Roller Hill. Our secondary objective is that it will have a modular payload that will be removable so that we can exchange out sensor suites and scientific equipment based on what the mission objective is. So this is the overview of ROLR. Well, here we have our base station that will send power to our electrical and control system. This electrical and control system will send power to our structural system and our communication system. In turn, that communication system will send data to our operator, and the operator will send commands to our electrical and control system, and that'll be our cycle. This is our concept of operation. So it starts with phase 1, and it'll conduct system checks to make sure all of our sensors are working, and then once we get all of those checks done, we'll deploy from base. That'll lead to step 2, which is when ROLR will travel through the mission area along Roller Hill and back. During that time, it will be collecting a video feed and communicating that video feed and other data with the operator. Our third phase is that it will return to the base and initiate a recharge within our base station, and that will go back to phase 1, and we'll do that as many times as necessary. This is the basis of our concept design, and each subsystem will be going through their individual components. The yellow you'll see is the communication subsystem. All of the communications components are in yellow. Those will include the data modems and any transmitters and receivers. The power and control are both covered in electrical control subsystem. Our power system is any power sources and power storages we have, and the control is any drive mechanisms that we have. And lastly, everything else, the brown and the silver, is the structural components, so that'll be the shells, the skeletons, and the different modules. So to cover our system requirements, the first one is that ROLR should be able to complete 1 mission cycle, and that's a full circle of concept operations on 1 single charge under its own power. So it shouldn't have to recharge in the middle of Roller Hill. It needs to be able to do that 10 times. without any kind of failure, whether that's structural, power source failure. It'll incorporate all non-consumable components, which will be inside of the sealed body and head modules. And this will include our enclosed drive system, so everything will be inside of this module, and Braxton will talk about that in a second. It will return to a base station to be charged, as we covered earlier, and it will be remotely controlled by an operator, and that's just to simulate a planetary surface where our operator won't be on Mars with ROLR. It'll be separate. It'll potentially be on Earth away from that. ROLR will collect and transmit scientific and operational data, and that's the video feed, any temperature sensors we need, and it will do all of this by November 12, 2019, which is the end of our detail semester. I'll now be passing it off to John Daniels and Braxton Kendall, and they will be talking about the electrical and control subsystem.
Thanks, Nicole. I will be going over the electrical and control subsystem requirements and design drivers, as well as the design of the base station and power components. So the electrical and control subsystem requirements are the ability to be able to recharge, as well as to have enough capacity to complete one mission cycle, and to be able to also continue to do more mission cycles up to 10. The base station will have the capability to recharge ROLR, to receive power, and to remain independent of existing infrastructure. For the rest of our requirements, we have the locomotion of the body module, as well as attitude control of the head module via remote control. We will be able to collect scientific and observational data for 10 mission cycles. We will also have a head module that will have a live video system and will not go below 20 degrees of vertical. Some of the design drivers that we have at this time are, due to the lack of power outlets and other power sources, we're going to be using a solar panel to receive power to be able to fill the battery that is going to be within the base station, and that battery will subsequently be able to recharge our actual ROLR itself. Also, experience. Our team has experience with turnkey batteries, as well as the PID feedback loops. Also with feedback loops, we found that the PID feedback loop is much quicker than an LQR, so we're going to do this because it's much more time efficient for what we need at this time. Our hamster drive, we're going to be using an enclosed drive system because we have a spherical shell. Also price, we found around campus some E-Flight Power 60 motors, and those motors will also be able to fit our motor requirements, as well as the 1/50th gear ratio that we'll be using. So here we have the base station. We have a 12-volt, 100 amp hour AGM deep cycle battery, as well as a 100-watt polycrystalline solar panel. Both of these will be able to charge ROLR so that it can conduct its mission cycles. And lastly, we have a power storage device. I already mentioned the turnkey batteries. We'll be using 3 5,000 milliamp hour batteries. We'll have 1 in the head and then 2 in the body. Next, I'll be passing it off to Braxton so he can cover the rest of the electrical and control systems.
Thank you, John. So my coverage of the electrical and control system will consist mainly of the drive system choices that we've made as far as design is concerned, as well as the control method for the head attitude. So starting off for our drive mechanism, we're going to be employing a hamster drive configuration. That's the configuration where we have two wheels on either side of the top level of this sled. They're going to be powered by 2 E-Flight Power 60 brushless outrunner motors. The brushless is very important, as brush motors have graphite brushes that will decay over time, which can, in our closed system, eventually lead to possible electrical damage, as graphite is conductive. And then with our motor selection currently, we did not originally have the torque requirement met in order to move rollers, so this will be employing a 1 to 50 gear reduction in order to give us the required torque to traverse up and down roller hill with no issues. So as you can see here, we have the 2 wheels on either side of the sled. The E-Flight Power 60s are modeled here with our gear reduction and casters not being modeled as of yet. That will be added on after further development. But the gear reduction will take place in between the motor output shaft and the wheel axle here. In addition, we will also have 2 stabilizing casters positioned 90 degrees away from these wheels. That's in order to make it so there's no wobble of the sled, as it will be free floating inside the actual ball module. Next up came our design of the motor, and we essentially chose the E-Flight Power 60 because we had them available here on campus, so that was a big reduction in our cost for the overall roller project. They run at 470 kV. For those of you who might not be familiar, that's RPM per volt. So with our max voltage of 12.6 volts at 470 kV, we can expect, before the gear reduction, about 6,000 RPM output. With our gear reduction, that will increase our torque at a 50% throttle state to about approximately 8.45 foot-pounds of torque and reduce our output RPM to 118.9. And with that and the dimensions of rover, that gives us roughly 8 miles an hour at 50% throttle state. For the head attitude control, it consists of 3 parts, 2 servos, one located at the bottom of the control shaft here in the center, and that's going to be to control the traverse of the actual control shaft. There will be an IMU located on the shaft with gyroscopes and accelerometers in order to measure our attitude and make sure that we are maintaining within 20 degrees of vertical as per our requirements for the electrical and control subsystem, as well as a servo for rotation here at the top of the shaft that will control the rotation of the head module via the shaft. And then on top of that, there will be 3 magnets located at the top, which will be in alignment with 3 ball transfer units and 3 additional magnets here in the ball module, and that will allow for seamless traversal of the head module over the ball module. And in order to maintain our desired attitude, we're going to be employing a PID feedback loop. Over the summer, one of my big projects is I'm going to be doing the tuning for the drive control and then taking all of the physical parameters of roller and being able to model that. And now I'll be passing it off to Austin McCoskey, who will be going over our communication subsystem.
Thank you, Braxton. As Braxton said, I'll be going over the communication subsystem. There we go. First off, this set of requirements dictates how roller will actually transmit data to the operator. Roller must be able to communicate effectively our operational and telemetry data over the entire range of roller hill for a duration of 10 mission cycles. The second set of requirements dictates how the operator must receive those. The operator obviously has to be able to receive that data and use it effectively to control roller remotely. The design drivers for the communication system mostly stem from ease of integration. For that reason, we decided to go with hobby-grade components, which usually have good documentation. They're usually less expensive and easier to work with because of that good documentation. Again, we have experience with some of these components, making them easier to work with. To satisfy the live video requirement, we're going to be using an eSheen 1000 TVL analog camera. That stands for TV lines. It's a measure of resolution. This provides us a low latency analog signal that will be conveyed back to the operator using an analog video transmitter so that the operator can view this video feed and effectively control roller remotely, even if it's out of line of sight. The video transmitter we've decided to go with has, even in non-optimal conditions, it has a range of at least 1,500 meters. Roller hill at its maximum distance is about 350 meters. And the operator will use a video receiver to receive that data and again view that video feed. Since we don't have any electrical connections between the ball module and the head module, we need a way to easily facilitate data transfer between the two. For that, we've gone with some low-power, low-range Bluetooth modems, again, just because they're so easy to work with and they have good documentation. They can take a UART standard serial data input and transmit that over Bluetooth up to the head, where the rest of the data is concatenated and then sent out to the operator using the telemetry modem. This telemetry modem again takes all of ROLR's operational and scientific data and conveys it back to the operator over 915 megahertz. I'm sorry. To control ROLR remotely, we're going to be using an RC transmitter and receiver pair. These devices were selected primarily based on their frequency of operation. Since we have so many RF devices operating in such a close proximity, we need to make sure nothing's going to overlap. For that reason, we went with a 433 megahertz control system made by EZUHF and a programmable transmitter to go along with that, which will allow us to do some of that custom motor mixing to get the right translation and rotation out of ROLR. And with that, I'll be handing it off to Kyle to cover structures.
Thank you, Austin. So to start off structures, I'm going to go over some requirements. The structure system needs to be able to have enough traction on the shell to make it uprollable. It also needs to be durable enough to withstand 10 mission cycles. The internal structure of the body module needs to be able to facilitate the head module control, which Braxton covered earlier with the servos. We need to have the head module stick to the body module, and we also need to be able to pull it off to satisfy our secondary objective of having a modular payload head. And then the base station needs to stay where it is so that way we know where it is when we come back. Some design drivers are price. The shells that we were looking at originally for one of my trade studies, we were looking at acrylic, bought from California Quality Plastics, and a fiberglass company, and they were half our budget at $500, so we had to go deal with stuff that we can make in-house. So we started looking at composites. I'll go over it a little bit more later. The base station structure will depend mostly on what budget we have left over after we build the main rover. The RF transparent, so that way the comms subsystem can control ROLR without any impedance, so we get a good signal that way. We wanted to mitigate some stresses in the composite shell, so we developed a skeleton, which you can see on the mock-up. And we wanted to make sure that the internal structure of ROLR is stable, so we wanted to lower that center of gravity using either probably both a counterweight and several layers of plexiglass to lower those components, so we get a lower center of gravity. And then the skeleton of ROLR, since we're already using one, we might as well 3D print it and come up with a well-designed fastening method for the hemispheres. Start off, we'll talk about the body module shell, and if I can have Austin assist me with the connection method. We're going to have 32 longitudinal spars, which are the red, blue, and gray, and then we'll have four longitudinal spars, which are the Lexan, and we have a built-in connection method where we can twist it off, pop it open, and work on any components we need when we need to work on them. And then the skin will go on the internal and external of that skeleton, 2 17-inch for the external components, and then 2 16 inches for the inside of ROLR, which the wheels will be rolling over. For the rest of the sled, we will have an internal structure, which you can see with the foam. It will be 3 plexiglass layers, 2 aluminum bars, 1 to hold the plexiglass layers together with the components, and 1 to facilitate the head attitude control. We will have 3 1.25-inch neodymium magnets to sit on top of the bar to attach to the head module to keep the head module where we want it. The head module will have the 3 1.25-inch neodymium magnets as well to pair with those in the beam. And then we will also have 3 ball transfer units to ensure that the body module can roll underneath the head module with relative ease. And now I'll be giving it to Ben for some conclusions.
All right, thanks, Kyle. So first, to close this out, I'm going to go over what kind of requirement satisfaction we're looking at in this stage of the project. So first off, we have 3 different categories. We have fully satisfied, which means all aspects of that requirement have been satisfied. We have partially satisfied, which means 1 or more aspects have been satisfied, and we have not satisfied, which means at this time none of them have been satisfied. So this doesn't actually reflect the final design, it just means we haven't done an analysis at this point to prove that the final design will meet this requirement. So in the interest of time, I'm only going to go over partially and not satisfied requirements. So to start us off, we have the partially satisfied requirement of 10 mission cycle durability. This is not fully satisfied because while we have analyzed most of our components, we haven't analyzed all of them yet for the durability of 10 mission cycles. Next, the seal structure is partially satisfied. ROLR is designed to be sealed, but we haven't had the chance to test it since we just have a skeleton at this point. We can't actually check it and make sure it's sealed. Next up, base station recharge. We know that our battery and our solar panel will be capable of recharging the battery. However, we haven't looked at our wireless charging method. We haven't done any analysis to verify that that is feasible. And then we have our 10 mission cycles by 1 month before the end of classes. That's not satisfied at all because we don't know how long this is going to take to fabricate. Next, electrical and control. We have the partially satisfied requirement of power rechargeability. And again, the same reason, we don't know if our wireless charging will be capable of recharging roller yet. We haven't done an analysis to do it. Then our electrical data, that's partially satisfied because our comps will be able to communicate with roller, but we don't know what kind of data we're going to be sending exactly, quantity or quality. And then we have our electrical durability. That's not satisfied at all because we haven't looked at the durability of our electrical components. And then we have the stable head requirement, and that is currently partially satisfied because we've decided on a PID controller that in theory is capable of providing the proper stability. However, we haven't tuned it yet. Next up for comms, the only partially satisfied requirement in this is the communication link, and that is partially satisfied because we don't know again what kind of data exactly the operator is going to be receiving. Finally, we have structures. Traction is completely not satisfied because our use case roller hill has not yet been analyzed for what kind of coefficient of friction or tractional properties we're going to need in order to climb roller hill. Then we have our structural sustainability, which is partially satisfied, and that is due to the fact that we haven't looked at all the aspects of roller to make sure that it can withstand the 10 mission cycles in terms of structure. We have done a static analysis, but we haven't done a dynamic analysis to make sure that under actual rolling conditions, it will withstand the forces that it has to. Then we have our head module support. That's partially satisfied because all of it has been designed except for the actual beam that modulates roller's head. The beam, we don't have this thing, but in there, the foam beam. We don't actually know what that's going to look like yet, so we can't completely say that that's fully satisfied. And then we have the stationary base. That is partially satisfied because while the base station isn't designed to move, we haven't done any kind of analysis that proves that it won't move under any kind of conditions like wind or some kind of upheaval. So this is a look at our budget. The important aspects to take away are that, surprisingly, the numbers work out to exactly 800 right now. That's given us a 20% margin. We used to have a 15% margin, but we had some change in cost and some free items come into us, legacy hardware, which has moved our margin up to 20%. We expect it to continue to change. However, we do not expect to exceed our current budget. Future items, we're going to be looking at our objectives and requirements very closely this summer, rewording, restructuring, and maybe moving around or eliminating some of them in order to make them a little more conducive to the typical standards of systems engineering. And then we're also going to be evaluating the complexity of our system. We have a lot of different parts here, a lot of things that have to coordinate together, and we're going to try and take a hard look at that and make sure that it is in fact feasible for the time constraint and budgetary constraints that we have. So now I want to cover the lessons that we've learned this semester, guys. It's been a long semester, and we've had a lot of challenges that we've had to overcome and a lot of lessons that we've learned from this. First, we've had the big one of time, which I've heard other groups say today, and that is because that the longer you take to do something, typically there's efficiency to consider, of course, but typically the longer you take to do something, the more time you spend on it, and the sooner you start, the better quality of a product you're going to get out of it. Next, we have one about teamwork. That's communication, enthusiasm, and collaboration are essential, and that kind of plays into the next one of staying positive really helps others stay positive. Your attitude determines the attitude of those around you, and so if you want a project to come out well with everyone coordinating happily, then you yourself have to bring the attitude you want to see. And finally, something for technical writing is that advanced modeling, any kind of visual aid, something that can provide a picture of what you're doing rather than just text, goes a really long way to simplifying a complex idea. So finally, I'd like to offer special thanks to everyone on the following slides. In the interest of time, I won't say their names, but everyone here has been a significant contribution to ROLR in some way or another. One more slide of the names. And here's our references slide. All right, so now I'd like to open up the floor to questions and thank everyone for coming.
Panelists, it looks like we have plenty of time for questions. I think we're roughly 20 minutes or so.
Oh, goody. It would have been nice to see a kind of a diagram of the system architecture and like who's, in charge of what. You kind of had the names here, but like you said, a picture's worth 1,000 of them. one thing, my name is Sarah Hatch. Graduated here in '03 and have been working at the Jet Propulsion Laboratory for the last 14 years. MSL has well more than one payload. Little nit there.
Okay.
But you kind of mentioned to have multiple payloads in the head or having multiple heads that you can interchange, but you didn't discuss what kind of payloads those would be. I missed it if so. And the requirements here are a little lacking for me in terms of one of the other senior teams earlier today had their planned route, if you will, change on them a half dozen times, which cost them time, energy, money. So you don't specify what roller hill means. You kind of say you're going to do this, but it doesn't talk about distance, incline, the environment that you're going to be encountering, whether it's grass, cement, dirt. So there's a lot here that you could encounter if they say that you can't have this little piece of real estate that you're banking on. And that kind of goes to the 10 instances of going back and forth. That seems extremely ambitious. I'd say, you know, in primary goal, do it once, and tertiary or secondary, do it more than once. But 10 seems extremely ambitious. Let's see, I got more. It would be nice to see schedule milestones. You talked about in your last couple slides there of we don't know how long this is going to take, but what you can do is think ahead about what pieces and parts need to be going where, and you can plan out a schedule and say, okay, if by spring break we haven't gotten this done, then we're in trouble. And so you can kind of plan around also what all the other teams are doing. Another team had kind of mentioned that today, that they wanted to get in before spring break, but the AbFab was busy. So having a plan and schedule margin would be a good thing to have. Let's see here. There also wasn't very much about weight, CG location, volume. I mean, I think you know planned out what some of these things are, but you don't have requirements on them. So it seems very willy-nilly haphazard of you're kind of flying by the seat of your pants designing this thing, hoping that it'll work and not working to an actual what you know your sponsor is saying that he can provide. So if this is going in a payload bay of Dragon, or if it's up inside a rover, you need to have some sort of volumetric requirements and mass to work to. And I didn't see like you had your mass equipment list of 11,000 kilograms, or actually it was dollars, I think.
11,000 grams. 11
Yeah,
kilograms.
there was a dollar sign in front. So, but you got to have those things worked out so that when whoever's designing the head fits on top and it's 3 times the weight, you got to be able to work on that on whoever's the interface. And same thing about like depth of discharge, the memory storage, the data rates. You might not have had an understanding of what those were going to be, but at least have something written down that seems reasonable, so that when you find the actual part that you're going to use, you can compare it against that, and you can always refine these requirements based on feasibility and working with all the rest of the system. I didn't also see how many hours you guys have worked on this in the backup presentation. All the other teams had a little pie chart of what hours were worked when by whom, and sorry, it's just like blurting stuff out of you. And also, how much autonomy are you going to have in this? You kind of mentioned if you're on Mars, you can't joystick it. You've got 7 minutes or 14 minutes to wait for it to do something. So the level of autonomy, I think, would be, again, ambitious for you to take on. But if you mention it, you might want to say that you purposely did or did not look into it.
Yeah, I mentioned it briefly in the head attitude control, but one of the requirements for the head attitude controls is going to remain within 20 degrees of the vertical axis autonomously, and currently that's currently the only autonomy that is planned on, and the rest is going to be RC.
All right, guys. Good presentation overall as far as your transitions, your voice, your tone, everything. It was easy to listen to. The the presentation itself was a bit cluttered at times with some of your graphics. There were a few too many arrows going in a lot of directions. There were a few too many, little text heavy on some of the slides. All right, don't get me wrong. I love the fact that you guys are building BB-8. That's awesome. It's super cool. The hard reality here, I guess, is that there's a reason a circular rover has not been built, and that's because the design inherently suffers from a lot of problems, and I didn't see a lot of those addressed. You did mention the fact that you're going to struggle with traction on the hill, and I'm going to tell you right now that's going to be one of your biggest concerns, because you have a smooth ball on a rough surface, and if you get it in sand, if you get it on grass, if you get it anywhere, you're going to have traction control issues. The issue with that is that if you make it grippy, then the system fails inherently, because your head unit is not going to be able to slide over the ball. So that's one of the grave design concerns right there. The other concern is that if it does pick up any foreign debris on the surface, that's going to bind up and cause you problems on the head unit as well. And during the presentation, I unfortunately wasn't sold on the modularity of the system, because you didn't mention it. As she mentioned, you didn't mention what the advantage is over some other rover systems, which are very rapidly interchangeable and can carry a host of scientific payloads for a very long period of time, have interchangeable articulating arms. I mean, there's a lot of different tasks that modern rovers can perform. So I'm just not sure that this one stands up. So that's just something where you might want to change the track you're going with this of, you want to change it to a technology demonstrator, maybe, more than a advanced alternative rover, right? Because it's going to be a hard sell as a more advanced system, but it is neat and interesting as a technology demonstrator, right? Again, the choice of roller hill, it felt like you picked the hill and then tried to decide why you picked the hill, and that's not the way to perform testing, right? You want to set up what the parameters you want to test are, and then you want to select your test location. Okay, so you have the hill laid out, but I didn't see anything in there about the topography. Do you know what kind of elevation change you're dealing with? Do you know what the slope is?
That was picked based on some parameters we got from a previous rover. I'm gonna get it mixed up, so I won't say which. But we wanted a 10-degree incline that has a 10.5. We wanted to emulate the total distance traveled by some of the other rovers, hence the 10 mission cycles. The 10 mission cycles in and of itself gives us a distance that was traveled in total by one of the other rovers. It equates to 4 miles. Again, I won't say which, I'm gonna get it mixed up. But we actually currently have the battery capacity to do all 10 of them at once. It's gonna be a matter of structural durability and making sure we have enough traction to get up that hill. But we did pick the hill based on some parameters we had in mind, but we didn't explicitly say that. I agree we should put that in there.
Okay, yep, just make sure you mention that, and that's gonna help a lot, as opposed to, hey, we found a nice hill we like it. Yeah. Okay, someone on your team likes CAD. Who's good at CAD? It looked good. The CAD was great. CAD is not the entire design, however. So be cautious with that, because you had a lot of awesome CAD, but I feel like there was a lot of time invested into that, and not as much time invested into material studies and also communication studies. And thinking about one thing that struck me, you use a neodymium magnet to hold your head unit on. Magnets cause a lot of issues with scientific payloads, especially sensitive electronics, and you have one parked right there. That has to be, by its nature, has to be pretty robust. So have you considered the magnetic environment and thinking about some shielding and making sure that your communications aren't inhibited?
Yes, so to go along with that, the inductive charging coils that we're looking at selecting have ferromagnetic shielding, and their proximity to the magnets, one, helps shield not only the coil, but the magnets as well. According to Lenz's law, a static magnetic field shouldn't interfere with a dynamic magnetic field, one that's changing with time, if you will. And given their proximity to the rest of the communications components, especially the antennas being normal to those magnets, we don't expect significant interference. I did talk with one of the EE professors on campus to get his opinions on that, and he didn't feel that there was concern warranted by the proximity of those magnets, other than with that IMU. The IMU is inherently susceptible to magnetic fields. That's something we're going to have to especially shield against.
Okay. The other question I had is talking about your range. The way you're testing your range is to go back and forth on a hill. You know, make sure that you can maintain or that your battery will sustain you over your range, which is great. But it doesn't tell me if your communications will be able to sustain the range.
For the sake of time, we actually had a much longer presentation we gave last week, in that we did detail all of our analyses. I performed a link budget analysis on what I thought was the weakest link, the lowest power, highest frequency component that would propagate as well. With that, we got a maximum effective range of 860 meters. So given our max range of 350 meters, and that being the weakest link, I think all the other components should satisfy that.
All right, sounds good. All right, I think that's everything that I have. Good job, guys.
Thank you.